This is going to be the third video of a series of videos. This is probably going to be the final one. I'm going to probably switch to shorter formats after this, but there may be one more. So in this video, we're going to go over preparation of carboxylic acids, acidity, reduction, esterification, and conversion to acid chlorides, and decarboxylation. So let's first go over what a carboxylic acid is. So the functional group of a carboxylic acid contains a carbonyl group and a hydroxyl group. So you will usually see it written as COOH, or sometimes it may be written as CO2H. So the structure will look like generally like this. Excuse me. Where this is the carbon, the first oxygen, second oxygen, and the hydrogen. So there are some general formulas for carboxylic acids. So aromatic carboxylic acids will usually be written like so, COOH. Aliphic carboxylic acids will be written as RCOOH. And alpha and beta unsaturated carboxylic acids are RCH2, CH2COOH. So let's move on to the nomenclature that you will probably see with carboxylic acids. So the E, normally alkene in a carboxylic acid, the E is dropped from the parent alkene at the end, and the suffix oic acid is added. So alkane, the E will be dropped, and the suffix OIC, acid, is added. So the chain will be numbered beginning with the carbon of the carboxyl group. So we'll go over the structure later. So some common names that you might see carboxylic acids as are formic acid and acetic acid. They are the common name will be retained. So formic acid will be methanoic acid, and acetic acid is ethanoic acid. If the compound contains a carbon-to-carbon double bond or a carbon-carbon triple bond, you will change the infix from AN to EN to YN, just like alkenes, and alkynes, just like normal. So let's say we have acrylic acid. It's just a double bond here. This will be propanoic acid. And this is actually acrylic acid. And if we have something like this is crotonic acid, but the nomenclature for this acid is going to be trans to butanoic acid. So the carboxyl group will take precedence over most other functional groups. So you will want to, that carboxyl group will have higher priority than most other functional groups in the compound. Let's go over the dicarboxylic acids. So dicarboxylic acids will be named by adding the suffix dioic instead. Oxalic acid. And that would be just added to the carbon chain that contains both carboxyl groups. So let's say we have a compound like so. This will be ethane dioic acid. So you might see this as oxalic acid, but its formal name is ethane dioic acid. And notice that we don't drop the E at the end there. So if the carboxyl group is bonded to a cycloalkane ring, the compound named is usually will be added to carboxylic acid, a suffix to the name of the ring. So say we have 2-cyclohexene. Well, if by itself it would not be 2-cyclohexene, it will be 1-cyclohexene, but because that we are adding a COOH, this will take precedence, so this will count from here. So this would be 2-cyclohexene carboxylic acid. Let's go over some other stuff. Benzoic acid will be the most simple carboxylic acid. There are some derivatives of benzenoic acids that you might want to know. So numbers will be used to show the location of substituents relative to the carboxyl group. So benzoic acid will look like this. You can use a number to show the substituents. So if I had an OH group here, will be relative to the carboxyl group. So this will be 1, and that will be 2. So this will be 2-hydroxy benzoic acid, and otherwise known as salicylic acid. If we had, say, another COOH group here, this then will be 1,2-benzene dicarboxylic acid. So benzene dicarboxylic acid. I'm not gonna write it out, but you get me. So if we had a COOH group here, this will be 1,4-benzene dicarboxylic acid. So as you can see, if we have two carboxyl groups, sorry, that slipped my mind for a second, the word dicarboxylic acid will be added to benzene. So When common names are used, the Greek letters alpha, beta, will be so forth will be used as prefixes to locate the substituents. So it'll look like this. If we had, say, like this, and this will be 1, first carbon, second, third, fourth, and fifth. So let's say we had an H2 here, so this will be aminobutyric acid, otherwise known aminobutyric acid, and this will be 4-aminobutyric acid, 4, otherwise known as GABA. So 1 will be alpha, beta, and like so. So if this the formal name for this will be 4-aminobutanoic acid. But if we use the common name of this acid, aminobutyric acid, this is going to be with zeta. So zeta aminobutyric acid. Delta aminobutyric acid, sorry. Right, let me write that down. Delta aminobutyric acid, otherwise known as GABA. Let's go over another one. If we had something like so, I'm going to start naming from here, 1, 2, 3, and if we had an AH group, H2 right here, this will be the standard name for this would be S2-aminopropanoic acid. But the common name for this would be S2 alpha. Sorry. S2 alpha aminopropanoic acid, otherwise known as L-alanine. And I just realized I numbered this chart wrong earlier, but it should look like this, where you start from here. The Greek letter names are not really references to are basically like references to the carbon, similar to this, but it doesn't start. It starts from the first carbon after the carboxylic carbon. So it's like the alpha carbon, the beta carbon, the alpha carbon, the beta carbon, the gamma carbon, and the delta carbon. So this would be the delta carbon, but this would be the gamma carbon. So this is actually gamma aminobutyric acid. So let's move on to the presence of a ketone, carbono, in a substituted carboxylic acid is indicated by the prefix keto. So the acetyl group CH3CO or AC. So if we had a compound that looked like this, this would be 3-oxobutanoic acid. The common name for this would be 1, 2, 3. So this will be alpha, and this would be beta. So this will be beta ketobutyric acid, otherwise known as acetoacetic acid. There are several names and derivatives for various carboxylic acids. We're not going to go over all of them, but you could look. There are charts out there with it to look up if you want. So let's move on then to the physical properties of some of carboxylic acids. So, sorry, excuse me. Carboxylic acids are usually associated by hydrogen bonding to dimers in liquid and solid states. So, carboxylic acid, like so. This carboxylic acid here will hydrogen bond like so. By charge attraction with itself, as you can see here. So this gives carboxylic acid its higher boiling points than other types of organic compounds. And of similar molecular weight. So this results from their relative polarity and their ability to form pretty strong intermolecular hydrogen bonds. So yeah, and these carboxylic acids will be more soluble in water than alcohols, and alcohols, ethers, aldehydes, and ketones of similar weight, because it will be able to form hydrogen bonds with water and OH, with their CO and OH groups. So there are charts as well going over the boiling point and solubilities in waters of selected carboxylics, but we're not going to go over all of that right now. So usually, as normal, the solubility in water will decrease as molecular weight increases. The hydrophilic carboxyl group will increase water solubility, while the hydrophobic hydrocarbon chains will decrease water solubility. So if we had a very long hydrocarbon chain, like say something like this, this will not be as soluble in water compared to if we had just something like this, which is what we have up here. Liquid carboxylic acids, from propanoic acid to decanoic acids, have very foul odors. They smell very bad. So let's go through the actual acidity of carboxylic acids. So carboxylic acids are weak acids, and their Ka for most unsubstituted aphilic and aromatic carboxylic acids will be around Ka will be around 10 to the negative fourth to 10 to the negative fifth for most unsubstituted aphilic and aromatic carboxylic acids. So, greater acidity of carboxylic acids will be related to alcohol because that would because of delocalization of the negative charge of the carboxylate ion through resonance structures. So, and it will also be due to electron withdrawing inductive effect of the carbonyl groups. So, let's go through here. This is the resonance structure of a carboxylic acid. This is just going to be resonance with some of this. Like so. So the if we had chlorine in carboxylic acid, the electron withdrawing ability of something as negative as chlorine will be able to stabilize the anionic charge of the by electron withdrawal through bonds. Through sigma bonds, sorry. The strength of the inductive effect will be proportional to the number of chlorine atoms present. So let's go over an example. So if we had, say, this is acetic acid, the pKa of this will be around 4.76. But if we have chloroacetic acid, we just add 1 chlorine to this. The pKa will drop to 2.86. And if we have 2 chlorine, if we have dichloroacetic acid here, the pKa will be around 1.48. And if we have 3 chlorine with trichloroacetic acid, the pKa will be around 0.7. So the acidity will increase the more chlorines you attach on. The formation of carboxylic acid presents in an aqueous solution will depend on the which form the carboxylic acid will take in a aqueous solution will be dependent on the general pH of the solution. So let's just draw this. This will be the predominant species of carboxylic acid when the pH of the solution is less than 2.0. But as we get more acidic, basic, we're gonna see a equilibrium between both forms of carboxylic acids, like so. And when the pH is 7 or above in a basic solution, the predominant species will be this form here. So carboxylic acids, whether soluble or insoluble in water, will react with sodium hydroxide, potassium hydroxide, and other strong bases that will give water soluble salts. So benzoic acid is not very soluble in water. But if we were to add that to sodium hydroxide and water, it will give us sodium benzoate, which is very soluble in water. Like that, like so. So other than that, they will also form, carboxylic acids will also form water-soluble salts with ammonia and amines. So if we had ammonia and water, it will form another water-soluble salt, ammonium benzoate, like so. So let's go over the reaction of carboxylic acids with bases. So it will react with sodium bicarbonate and sodium carbonate to form water-soluble sodium salts and carbonic acid. And the carbonic acid will break down to carbon dioxide and water. So that's how the water-soluble salt is formed. This is another water-soluble salt that could be formed. The acid-base properties of carboxylic acids will allows us to have an easy separation of carboxylic acids from water-insoluble non-acidic acidic compounds. So, for example, if we had benzoyl alcohol and benzoic acid, and we dissolve both in ether and mix it with sodium hydroxide, we'll be able to separate the benzoyl alcohol from the ether layer and the benzoic acid from the water layer, because the water-soluble salts forming with sodium hydroxide. So this allows us to be able to separate carboxylic acids from non-acidic compounds, water-insoluble. No. Let's move on. Let's move on to the preparation of carboxylic acids. How do we prepare carboxylic acids? Usually they will be prepared through, well, not usually, but they can be prepared through carboxylation of Gregory reagents. So this will be an overall conversion of acyl or aryl halides to a carboxylic acid. So this will involve the treating of a Gregory reagent with carbon dioxide, and they will be able to obtain. We're going to be able to obtain the magnesium salt of the carboxylic acid, and we can protonate that magnesium salt with aqueous acid, and that will give us a carboxylic acid. So, if we have this Gregory reagent here, and we treat it with carbon dioxide, this is gonna, the nucleophilic carbon is gonna go for the electrophilic carbon, and that bond will break. Well, the double bond will no longer be a double bond, and this is gonna become something that looks like this. And if we were to add this to water, or if we were to protonate this or quench this, H3O plus, it's going to give us our carboxylic acid. Like so. And our magnesium, we'll get our magnesium back. So, let's go over how we can reduce the reduction of carboxylic acid. So carboxyl groups are very resistant to reduction, and they are not affected by catalytic hydrogenation under conditions that can easily reduce aldehydes and ketones to alcohols and alkenes and alkynes to alkanes. So the most common thing that you might see to reduce a carboxylic acid is LAH, which is lithium aluminum hydride. I'm not going to write out the whole thing because that would take way too long. Not really, but I'm just lazy. So this LAH is a very strong reducing agent. This will fully reduce a carboxyl group to a primary alcohol. So this is carried out in usually ether or tetrahydrofuran. So if we had CO, well, let's write it out. If we had this compound here, and we were to add this to LAH in ether and quench it with water, make sure to separate the steps because you do not want to mix LAH with water. That will not be great. That will actually turn that into a primary, primary alcohol. And it's going to form lithium hydroxide and aluminum hydroxide. So that's one way you can reduce a carboxylic acid is with LAH. So let me go through the mechanism. If you treat a carboxylic acid with LAH, it will form a tetracarboxylumin ion, and it will be hydrolyzed in water. That's what we need the water for. So if we had 4 equivalent of a carboxylic acid, and we were to add this to our 3 equivalent of, this is a balance equation by the way, of our LAH, this will form this intermediate, 4 equivalent of it, and this intermediate is going to be converted to something that looks like this. And 2 equivalent of lithium aluminum and 4 hydrogens, and this with water 4 equivalent of it. This will turn it into 4RCHOH. Just going to quench our product. Well, not so much just quench it, but protonate it. Hydroxide and our aluminum hydroxide, like so. Let's move on. Let's go over how we can selectively reduce the other functional groups. So carboxyl groups, because they are not affected by catalytic hydrogenation under conditions that can reduce aldehydes, ketones, alkynes. So we can use catalytic hydrogenation such as palladium over carbon with hydrogen gas, or sodium. This will not reduce a carboxyl group. So another one that we can use is sodium borohydride. This will be able to selectively reduce functional carboxyl group functional groups to alcohols and alkanes. Well, not carboxyl groups. They'll be able to reduce aldehydes, ketones, alkenes, and alkynes to alcohols or alkanes in the presence of carboxyl groups. So let's go over the let's go over the catalytic hydrogenation first. If we had a compound that looked like this, and we want to reduce this carboxyl group without reducing this one, we could use catalytic hydrogenation. We want to reduce this ketone. This is a ketone. We want to reduce that ketone without reducing our carboxylic acid. So we can use catalytic hydrogenation. So if we add hydrogen to this, usually you'll see palladium, platinum over carbon. This will be probably at 25C and 2 atmospheres, but you don't need to know this. It's just what the standard, what this might be run at. It will be able to keep our carboxylic acid group, but reduce that ketone to alcohol. So that is one way you can use selectively reduce carboxylic acids. The other way is with sodium borohydride. So aldehydes and ketones, carboxyl groups can be reduced selectively in the presence of a carboxyl group, using the less reactive sodium borohydride. So basically the same as what goes on here, except it's done with sodium borohydride. The mechanisms are different, but we're not going to go over that right now today. So next, let's talk about the Fischer esterification. So esters, esters can be easily prepared by treating a carboxylic acid with an alcohol in the presence of an acid catalyst. You might see that as sulfuric acid or gaseous hydrochloric acid. So the preparation of an ester in this form, this method, is called the Fischer esterification. So let's start with our favorite carboxylic acid. So we keep using this, but this one is just acetic acid, ethanoic acid. And if we were to add an alcohol in the presence of an acid catalyst, say sulfuric acid, we can form an ether like so, and water. So we can form an ether if we were to add a alcohol in the presence of an acid catalyst to a carboxylic acid. So as you can see, this reaction, the acid catalyzed reaction of esterification, is reversible. So the quantities of both the carboxylic acid and the alcohol remaining at the equilibrium during this reaction are appreciable. They're not that low. So Fischer esterification involves nucleophilic echo substitution. So if you control the reaction conditions, it's possible to prepare an ester with high yield with this method. If the alcohol is relatively inexpensive relative to the carboxylic acid, we can use a very high excess of alcohol in order to push the equilibrium towards our ester product. Or we can remove water through azeotropic distillation and a Dean-Stark trap in order to also push the equilibrium towards our ester product. So let's go over how we can synthesize methyl esters using a diazomethane. So diazomethane is CH2N2. This is a toxic chemical, and it's potentially explosive in air. And this diazomethane has a resonance structure, but you might see it like this. And we'll have a resonance structure like so. This is what diethylmethane will usually be represented as. So if we were to treat a carboxylic acid with diethylmethane in a ether solution, this will convert the carboxylic acid to its respective methyl ester. So if we have our favorite, let's just use a unnamed carboxylic acid. And if we were to treat this carboxylic acid in ester with diazomethane, it is going to convert it into a methyl ester. Like so, and it's going to produce nitrogen gas. So this esterification process occurs in 2 steps. We're going to go over the mechanism for this because it's pretty simple. First, the diazomethane will deprotonate the carboxylic acid. So there will be a proton transfer from diazomethane to carboxylic acid. Will and it will create a carboxylic anion. Let me show that here. And it will create a carboxylic anion. So this will deprotonate our carboxylic acid, and it's going to give us our carboxylate anion. Like so. And this is going to, in the second step, this is going to form a bond between the nucleophilic oxygen and the electrophilic carbon of the methyldiazolone anion that we've created in the previous step. So this is going to, so this is going to go for this oxygen. It's going to go for that carbon there. This bond is going to break, and in an SN2 reaction, this is going to create a methyl ester. And nitrogen gas, like so. So let's move on. Acid halides will be able to convert, well, let's go over how we can convert a carboxyl group to a acid halide. So acid chlorides will probably be the most frequently used acrohalide in the laboratory because they're relatively inexpensive and easy to prepare. So how can we convert a carboxylic acid to an acid chloride? We can usually do that by treating it with something called cyanochloride. So you might have seen this in Org 01. This is cyanochloride. And if we were to treat a carboxylic acid with this, it is going to create acid chloride. So let's just say we have our acetic acid, ethanoic acid, whatever you want to call this. And if we were to treat this with cyanochloride, it is going to give us our ethanoic chloride. Like so. So there are two steps in this reaction. The first step is going to, the thionyl it's going to transform the OH group, which is a poor leaving group, into a chlorosulfide group, which is a good leaving group. So the thionyl will transform this OH group into a chlorosulfide group. And HCl. And in the second step, there will be a nucleophilic attack from a chloride ion that will give us a tetrahedrocarbono addition intermediate, which will collapse to give us our acid chloride, SO2, and our chloride ion. So let's paint this out a little more. so. This is going to go there, and a chlorine is going to come in. Just gonna draw out the chlorine is going to come in. Chlorine ion, chloride ion is going to come in and perform a nucleophilic attack on that carbon, and it's going to form a bond with that carbon and form an intermediate that looks like this. And the negative charge is going to be on that oxygen. It's going to form this intermediate here. And this intermediate is going to collapse and give us our reaction, complete our reaction. Going to collapse and form this, and our acid chloride, and it's going to give us our products and the chloride ion. So let's move on to decarboxylation. We'll talk about this more probably in a later video, but we're just gonna go through it relatively simply for now. Excuse me. Most carboxylic acids, if we heat it to a very high temperature, it will undergo thermodecarboxylation. So that means it will lose a carbon dioxide from its carboxyl group. So if we were to heat this, it will lose its carbon dioxide here. And typically they are quite resistant to moderate heats and will melt or even boil without decarboxylation. But there are some exceptions, such as carboxylic acids that have a carbonyl group, beta to the carboxyl group. They will undergo decarboxylation very readily on mild heating. So something that looks like this. So if we have a carbonyl group on the beta carbon from the carboxyl group, this is going to decarboxylate very rapidly, very readily, if we were to heat this. In order to normally a carboxylic acid, this will be a very high temperature in order to decarboxylate a carboxylic acid. So let's talk about the thermal decarboxylation of beta keto acids involving the rearrangement of 6 electrons in a cyclic 6-membered transition state. So a cyclic 6-member transition state is going to first become a NO of a ketone, and it's going to become a ketone in a reversible reaction, but it's going to favor the ketone. So For example, let's say we have oxosuccinic acid. So here is our carboxylic acid group. And here, this is a tricarboxylic acid. So this intermediate in this the tricarboxylic acid cycle has a carbonyl in the beta position to it. So this will be the alpha position, and this will be the beta location. So the alpha keto version of this is going to look like this. So, this is this is alpha ketoglutaric acid, like so. Let's move on. Now we're going to talk about the decarboxylation of malonic acid and substituted malonic acid. So decarboxylation will occur if there are any carbonyl groups at the beta position. So if we had malonic acid, this will decarboxylate at around 140 to 150 Celsius into so the decarboxylation of malonic acids involves the rearrangement of 6 electrons in a cyclic 6-member transition state, as before. I'm not going to go over the exact steps because that would take too long, but there's only 2 steps, but that's a lot of drawing to do. So the first, I might do a more in-depth video on this later. But the first step will be a redistribution of 6 electrons in a 6-member transition state will give us our carbon dioxide and the NO form of the carboxyl group. And the second step will be keto-NO tautomerization of the NO, and it's going to give us a more stable keto form with the carboxyl group. So that's it for today's video. It's a relatively shorter video compared to before, but as I said before, this might be the last video in this series, but I will move on to shorter form videos containing more specific topic explorations. So these are just general overviews of these topics. So for next time, we're probably going to have, let me look at this. Next video is probably going to be on the hydrolysis and characteristic reactions with alcohols, ammonia, amines, some reactions of acid chlorides with salts of carboxylic acids, interconversion of functional derivatives, reaction with organometallic compounds, and reduction. So that will be a longer video if I were to do that, but However, I may chop it up a bit, or I might not even do them in the first place. So, thank you.